What you're about to see is an exclusive interview with one of the leaders of one of the most exciting observatories ever built, the Vera Rubin Observatory. In just 10 hours, you captured over 2,000 asteroids, which is something like 100 times faster than the discovery rate around the whole planet. Some of these asteroids could be Earth killers, and that same technology is set to revolutionize our understanding of dark matter, peering into the massive Virgo Cluster with unprecedented clarity.
When you finally see the observatory, not anymore as a CAD rendering, but as something that is the actual mountain, you walk through it and then you see the images, it's phenomenal.
This isn't science fiction. It's the brand new Vera Rubin Observatory, a testament to the groundbreaking science and legacy of Vera Rubin herself.
Vera Rubin comes along and realizes, oh yes, like this is really becoming an evidence for dark matter.
With a gigapixel camera and unprecedented data analysis requirements, Mario Jurić is here to give us an exclusive glimpse into the data that was just released.
Everything we talked about today, yeah, we're going to do that, but that's probably not what Rubin's going to be famous for. It'll be something that's completely unknown.
Prepare to have your mind blown and expanded, because what you're about to see is just the beginning. What it holds in store will take us deep into the impossible. Welcome everybody for what is an exclusive, as far as I'm aware, interview with one of the leaders of the Vera Rubin Observatory, who also happens to be a tremendous individual scientist, my friend, Professor Mario Jurić of the University of Washington, where he is the director of their Juric Center, which is a pretty awesome responsibility. But he's also responsible, and he and his group are responsible for the software that discovers time-varying and motion and objects in motion in the newly commissioned Vera Rubin Observatory. Mario, thank you for joining us, especially with this cool embargo data that we're about to reveal. Well, it'll be unembargoed by the time people are seeing this, but thank you so much for coming on the show.
Thanks for having me, Brian. I love the show. It's really a pleasure to show all this to you and to your audience here.
And I should say you've been a great citizen and help to the Simons Observatory, serving on our executive external advisory committee, which has been phenomenally successful, thanks in part to your leadership. So we're going to talk today about two aspects of just mind-blowing data that I've just had the opportunity to take a look at before we started the airing of the episode. And by the time people see this, it's right after the news conference, the huge news conference in Washington, D.C. And Mario, you've been having your own up there in Seattle. And we've just really blew my mind looking at just a tiny fraction of the sky and how you guys were able to discover an asteroid in just 10 hours. You captured over 2,000 asteroids, which is something like 100 times faster than the discovery rate around the whole planet in typical, days and nights and weeks and years. So this is going to be incredible. We're going to talk about that. And we're going to talk about an amazing fly through the Virgo Cluster, which is so incredibly granular that I felt like we could zoom in and see my house if I had a house in the Virgo Cluster. But before we get there, I want to get an overview from you. You've been working on this project for a long time. How does it feel to finally come to fruition? When you first saw the data that we're going to show the audience today, how did it hit you as a human being?
It feels great. My first conference on what was to become Rubin Observatory was as a graduate student in 2006. So I heard about it in 2005. And I had some of my undergrads point out, when I said, no, it takes a long time, but it wasn't that far ago. It was like in 2005. And one of my undergrads said, I was born in 2004. So that's how long it takes to build these. So when you finally see the observatory, not anymore as a CAD rendering, but as something that is on the actual mountain, you walk through it and then you see the images, it's phenomenal. It's like, this must be what rocket engineers or astronauts feel when they finally sit in that rocket and launch into space. Like, that's what I felt. And the data are great. Like, that's the best part of it. Like, you build something, it takes 20 years, but then when it starts, it just works. It's wonderful.
Well, the data really couldn't come at a better time. It's always a good time to get new data from a massive instrument like the Vera Rubin Observatory in Chile. But in particular now, when we see the standard model of cosmology coming under assault, and I think that, some of the data that you'll show and that your team and the other teams that will have access to this data, as will you out there, the audience, have access to it. I'll put links to the web browsers and other resources, because all this is for citizens too, right, Mario? This is not just for cloistered ivory tower denizens like you and me. This is for the whole world, correct?
Yeah. That's the cool thing about this observatory. This is one of the first projects that started this whole new, what's now normal. When we started with Rubin, the whole idea was we build an observatory that uses open software and delivers open data and enables open science. This observatory is, just maybe to give your viewers a little bit of an idea of what we're talking about, it's an 8-meter telescope, 8.4-meter telescope. That's in the class of these largest telescopes that we have around at this time. It's in Chile. It's on a mountain called Sierra Pachon, about 40 kilometers from the coast of Chile, in the Andes. Perfect place to put it. But what's different about it is it's not designed to zoom in on a single object and take a really high resolution picture of a single object. It's designed to take images very rapidly of very wide field of view, so we can cover the entire sky roughly every couple of days down there. And then what we do with this is rather than have one person ask for an image of a particular object and then spend some time going in and taking it and reusing themselves, because the telescope can cover the entire sky every 3 weeks, every 3 days, we effectively download the sky, we put it in the database, and we let anyone use those images. So what we kind of do is we allow the entire U.S. astronomical community, plus Chile, plus international partners, for every single astronomer in the country basically to have their own 8-meter telescope that just happens to have imaged the entire southern sky and happens to be doing that every 3 nights for the next 10 years. So that you can just go ahead and do it. And you don't even have to be a professional. Even amateurs can jump in on this. So that's really the hope. Download the sky, and we'll let anyone try to figure out any kind of science that they want to with this data set.
And that's what's so fascinating to me is, yes, as a kid, having access to a 2-inch diameter telescope, seemed like I was the captain of my own observatory. And now, literally, as you say, we can actually, treat this almost as if it's ours. It's not targeted. You don't have to submit proposals and so forth. So it's easier in some ways than the job that you had. And that's thanks to your hard work and that of the entire team. I want to talk about the, galactic neighborhood that we find ourselves in, the Virgo Cluster, our giant, massive collection of galaxies, over 1,000 of them, that Rubin has already observed in its commissioning data. Now, we should say something. What do astronomers mean by, first light look? Or this isn't by no means, all of what the Rubin Observatory is even comprehensively capable of doing. Talk about what were the data that we're about to show the audience. Where did that come from? How much total time elapsed was it on a calendar, say? And how much of the ultimate horsepower of Rubin is being displayed in what we're about to show?
Rubin has the largest digital camera in the world. It's 3.2 gigapixels. So I don't know what the latest iPhone is, probably like a few tens of megapixels. So you take that and times 100 or times a couple of hundred. Every image, every frame that it takes, that's how big it is. On the sky, it's roughly 3.5 degrees across. So you can put, what's that, about 6 or 7 moons. You can tile them across the Rubin field. So that's how ultimately we'll be able to cover the entire sky. Now, the first image that we took with this telescope after 10 years of construction was on April 15th. So that's basically 2 months ago. The images that we're going to show for first look have been taken 2 weeks, or in some cases less than 2 weeks, than that first image ever on a telescope. Now, those of you who have built telescope or used telescope know how both impressive and crazy this is. So usually it takes a couple of months to get everything tuned up before the images to start flowing from the telescope. But we managed to get it done in something like 2 weeks, to the point where we can take many images of a small section of the sky, and we picked the Virgo Cluster because it's littered with galaxies, it looks beautiful, and it allows us to test all the software in addition to let the public and all the scientists see that the telescope works. So we took about 3 fields of view worth of data. So imagine 3 images with this big camera, 1, 2, 3, slightly overlapping. I should say 3 pointings. And then we took about 1,800 images over those 3 pointings. When you add up how much time that took, the impressive thing is it's only about 10 hours. So when we run in operations, what we're going to show you, we can build up that kind of image in about maybe in 2 nights of observing. That is the sort of thing that when the telescope operates fully later this year, we'll be doing across the entire sky. So what we're showing you right now is just a small piece, and with emphasis on going very deep. But when the telescope is really operational, we'll be able to give you an image like that goes over the entire sky. When you look at this and you think to yourself, well, look how many stars, look how many galaxies. What you're looking at is about 500 times smaller than the ultimate data set. So what we're going to showing you is 0.2% of what we'll ultimately have.
Before my audience, goes crazy, screaming at the screen, wanting to see the data, let's take a look at the Virgo fly-through, which just kind of left me with a sense of vertigo, flying through it, zooming in on it. I know people are going to enjoy it. So this is about a quintillion stellar mass object, if you will. The Virgo cluster, about 1,000 plus 1,300 maybe galaxies in a cluster, not too far away, tens of megaparsecs away. And it has each one of which could be like the Milky Way, like Andromeda, 100 billion stars within each one, perhaps. And because of that, this just mind-boggling amount of dark matter. And so we're going to see things in it that we never saw before by sheer quantity, but also the quality of the images are just truly breathtaking. I mean, and then later we're going to talk about the time domain sky. So the first batch of scientific data that we're going to show from Rubin comes from the team that works on extragalactic and cosmology. And then Mario's specialty are time domain things that go, hopefully not bump into the Earth, but could, and transient astronomy and all the things that can change in time, including asteroids that we'll talk about. And you, reminder, can win a fragment of the early solar system, an asteroid fragment called a meteorite. You're guaranteed to win one if you have a .edu email address. If you go to briankeating.com/edu, or if you don't have one, you might win one at briankeating.com/YT.
Is everyone ready? Okay, first look. Here we go.
Yep, got the elliptical galaxy on the screen.
There we go.
Can we see like naked eye, like lensing, or is that a figment of my imagination?
Probably not at this scale, but if we started zooming in, I bet we could find something that's lensed. You could spend, and this is not a hypothetical, you could spend weekends staring at this image and just zooming and moving around.
I'm making it my Zoom background. I'm literally making it my Zoom background as we speak.
So in case you're wondering, there are between 5 and 10 million objects in this image. And I'm just going to pan and scan around a little bit. So what this big blob in the center, that's M49. That's the big supermassive elliptical galaxy. It has a massive black hole in the center. It's active in the radio. It's well known. It's at about 56 million light years away from us, if I remember correctly. And I'm going to, just to give you a sense kind of what you're looking at, look at this note down here. It says you're looking at 1/2 of the Rubin's field of view. So from left to right, like this is not even a full image of one single image of what Rubin can do. So let's zoom out. And now we're starting to see what Rubin field of view is. So it's from here to here. So let's imagine if I took a circle around here, like that's one Rubin field of view. And remember that I said that we took 3 of them and just added them together. And this is the image. So there's one up here, one down here, one down here, and this is our Virgo cluster. These are thousands, probably tens of thousands of galaxies and large galaxies that we can see, and then millions of smaller galaxies. So we can just go and zoom in at a couple of these places and see how deep this telescope goes. Now, note as I zoom in, how the resolution changes. This web viewing software that we have works the same way as Google Maps. You move in and you get better and better resolution. And you see even more and more objects. So this blob in the foreground is the M49 galaxy. There's a ton of things behind it. Like look at all these little dots. Each one of those dots that is behind this galaxy and its light is coming through us. Now, some of them are clearly extended. So these are galaxies of their own. Here's one. Some of them look just like dots, like stars, but they aren't. Most of these things that you see, the vast majority of these things that you see are even more distant galaxies. So everything here that you see is billions and billions of stars.
It's amazing. I'm just looking up some of the facts while you're talking about M49. It's the second most massive galaxy after M87. It was discovered in 1771 by Charles Messier, who was not looking for galaxies, right, Mario? He was looking for comets and things that could be mistaken for comets. And it turns out Rubin's pretty good at finding those too. We'll talk about those later. But I just looked up the mass of the black hole in the center, 565 million solar masses. It's 130 times bigger than our galaxies. It has 6,000 globular clusters. I'm sure we're seeing some of those here, right?
It's a galaxy with, I think, the most globular clusters.
That's right.
Of
150
anything.
In the Milky Way and 6,000 in M49. Amazing.
So some of these dots here are those globular clusters in the galaxy. And this is this is the thing, right? Now, all of us astronomers can take these images and take these data and go do whatever science we care about. If we're working on globular clusters, here's probably the best and deepest survey of globular clusters in this galaxy or around this galaxy. And the cool thing is we actually, don't name anything because M49 is, or we don't aim for anything in specific. We just take the entire sky. This M49 is just one of these big galaxies, but they're its neighbor over here. There are many other galaxies. So why would you just study globulars around M49? You can go and study them around everything. That's the idea with this survey science type work. So here's a nice galaxy with a spiral that looks like it underwent some kind of interaction. So now all these stars are getting stretched out and tidally torn away from the galaxy. Now we can move around, and look at this one. So there's something different about this galaxy relative to the previous one. Now, this is where I would ask my students, what is different about this galaxy? Look at its color. We're looking at M49 and it was yellow and not much is happening. That galaxy, in terms of new stars forming, is fairly dead. There's whatever formed, few new stars are forming. This galaxy is very much alive. Look at all these spirals. Look at all these blue dots. Whenever you see this blue teal color, what that tells you is their star formation. These are places where millions of stars are being born right now. And the fun thing to me is that, we can just look at an image like that and point and say, oh, star formation. Oh, look at how many stars are being formed. And then we can take our tools, we can get a little bit more quantitative about it, measure star formation in this galaxy, measure star formation in other galaxies on this image, and understand how stars form throughout the history of the universe. So this is the kind of thing that you can do, that we will be doing scientifically with these kinds of images. But at this point, it's just so much fun to be able to go around and just recognize all these phenomena that we've learned from textbooks or taught our students in textbook. But here's another one. This is a face-on spiral galaxy. I think this one's NGC 4535. It's a fairly nearby galaxy. I think this is about 50 million light years as well. It's a spiral. Our Milky Way might look somewhat like this. There's a little bit of a bar in the center, and then look at all these spiral arms. And where do the stars form? Look at all these blue dots. They're right on top of spiral arms. It's exactly what we expect. And then there's just almost no empty space in these images. Like I zoom in here, and there's another spiral in the background. And like all these dots are likely galaxies that are in the background. So it's just, we haven't, as I said, these are 3 fields of Rubin, and each night will cover about 1,000 pointings. So each night we get 300 times more in terms of area.
Is there any easy way to see what are, say, Milky Way stars, as you can in the Hubble deep fields or in the Webb deep fields with 6 or 8 pointed diffraction spikes? I don't see anything with diffraction spikes here.
These images. So here's a star. Anything that's very bright and round is likely to be a star. So in here, what you're going to see is, because this image, again, remember, we took 3 pointings, but a total of 1,800 images. So this image is what we call a coad. So you add all those images together, and every image is taken with a slightly different angle. So those diffraction spikes get averaged out into these kind of thorn-like patterns, if you will. So if I zoom in enough, you can almost, you can see them. There was a set of observations taken with diffraction spikes going in this direction, and then another set in this, another in this. And when you add all that together, you get these kinds of patterns. The other cool thing about this to me is, if you want to see a shock wave, this one's my favorite. So this here is, what are these called? This is one of the NGC, this is a well-known cluster, the NGC 4410 galaxy group. And all of these are interacting. So this galaxy is interacting with this one, and you can see this like thin bridge of stars going from here to here. And that's probably because these galaxies, definitely interacted, maybe collided. But the fun thing with this galaxy, when I zoom in, you can see these kinds of shockwave type shells of stars. These are all stars. These are millions and billions of stars that got shocked into this configuration as this galaxy interacts with the galaxies above it. I've seen this before in simulations, but to see this well on actual data is just phenomenal. So all these simulations that we're doing over the last couple of decades, now we're going to have literally billions of galaxies to test against. Anyways, it's just a phenomenal data set, and I encourage all of your viewers, you can go to this website, you can just go and browse it yourself. That's the neat thing about this. There are other things in here, like how color tells you how far objects are. Virtually, if you zoom in, anything that's red and faint, it's not red because it's intrinsically red. It's red because of redshift. It's red because of distance. So if you find a little cluster of red dots, that means you've likely found an extragalactic, very distant cluster of galaxies. I'm looking at these and just waiting for the high resolution to load. So that's more likely than not just distant cluster of galaxies.
What is the spectroscopic capability of Rubin? How is that, and what kinds of bands are used in the optical, and how far out do you go in either direction?
It's an optical telescope. It's photometric, so we don't have a spectrograph on it. There are 6 bands, U, G, R, I, Z, Y. So U is roughly near ultraviolet, G is roughly green, R is roughly red, and then you get into infrared, and then you get into 3 kind of levels of infrared, with Y bands being around a micron. Near infrared to near ultraviolet, we cover the entire visible spectrum. This is the capability that lets us, remember when I said, oh, look at star formation in these galaxies? And because it's blue, this teal color, that's the U band. Blue comes spectrally from the U band, because these stars become very, very bright in ultraviolet and kind of blue part of the spectrum. And we've got the band to detect that.
So before we move on to asteroids and transients and comets and all sorts of other things, I do want to spend some time thinking about cosmology and the possible, import of Rubin on the ever-evolving understanding of the Lambda-CDM model. Just posted a video with Kyle Dawson, who is the former spokesperson for DESI. And, he's makes a pretty strong case that Lambda-CDM, where lambda is a cosmological constant, is in trouble. And I do remember, one of the original titles for Rubin was LSST, and it was going to have a lot of things to say about Lambda-CDM. And that is now a component, the survey's name, if I understand it right. The LS is large.
Earlier name of the telescope was the DMT, the Dark Matter Telescope. And the joke is kind of an internal joke, because it was going to try to figure out what dark matter is, which is a big part of Lambda-CDM. And the other dark matter, which were these distant objects in the solar system that very few were found at the time, 20 years ago, when trans-Neptunian objects were still a new curiosity. So then there was a realization from 2 very different groups of astronomers that, hey, we can build a telescope where the same telescope is going to answer those 2 very different questions.
Yeah.
But going to cosmology, the idea with Rubin is that even before all these tensions started arising, we still have the big question of what is the 96% of energy in the universe. So everything we're seeing here, I'm just, as you were talking, I'm looking at this image, all this beautiful Gaussian interaction, so on and so on, that's just matter. That's just matter in photons. It's 4%. These galaxies here, in terms of just mass, what you see here is roughly 10% of what's actually out there, dark matter to matter ratio. So there's 10 times more dark matter here that we just don't see. And we infer it through interactions of these galaxies and through exactly the details of what these bridges between galaxies look like when they collide. So Rubin was designed to go and take large enough sample of galaxies through the cosmic evolution, through cosmic time, to try to answer what is the nature of dark matter, and then what is the nature of dark energy. So the idea is to try to see if dark energy actually is consistent with the cosmological constant, or if we have to modify the theory somehow. And as we were building the telescope, the evidence has started accumulating that there's something more than just plain old lambda. And the timing could not have been perfect. Towards the end of the year, we'll start collecting data. It'll take probably about a year or 2 to get to sufficient numbers to start replicating results that are coming from DES or from DESI. And then by the time, we get to year 4 or 5, something's really off with Lambda-CDM, we should be able to tell. And so like the timing is perfect.
I have a very, soft spot in my heart for Vera Rubin. Obviously, many people don't know she was actually here at UCSD in 1965, 66, and 67, working with Margaret Burbidge, my late great colleague, Margaret Burbidge. She was here for 2 years as a postdoc, and she actually learned how to do rotation curve measurements from Margaret. Margaret was the astronomer. Jeff was a theorist and didn't much care for cosmologists anyway, as I would later learn. But her, kind of proximity to Palomar Observatory here, where she would do research following in Margaret's footsteps in many ways. It's funny because I have plates that Margaret took of galaxies and spectra, of course, that she used to measure rotation curves. And Margaret published on this, but she never really made the connection that Vera and Kent Ford and others did. What is the kind of sentiment around, Vera Rubin and so forth? Is there any connection with her family? She had 4 children, I believe, and some of whom are very active in terms of promoting her legacy beyond, the Nobel Prize that she was snubbed for, which I mentioned in my book. But tell me about the connection to Vera Rubin and just on a human level, what this means to astronomer, not just, the technical, but also people that are underrepresented in astronomy as well.
This is the connection, right? You asked me about one of the big things that this telescope wants to, or this hope to achieve, which is some better understanding of cosmology, and that includes dark energy and dark matter. And when you learn about dark matter, you learn about Fritz Zwicky, and then you learn about Vera Rubin. And Zwicky had this quote unquote crazy idea that something's off. I'm looking at all these clusters; they're moving way too fast. Galaxies and clusters. There might be something there that we don't quite understand, but it's like one interesting curiosity. And Vera Rubin comes along and measures the rotation curves of a large set of galaxies, and then realizes that, oh, wait a minute, that thing that seemed to be like some odd curiosity in the beginning, I'm seeing something similar at a very different scale, and connects the two and realizes, oh yes, like this is really becoming an evidence for dark matter that's hard to sidestep or explain elsewhere. And she just starts this whole, I think, revolution in our field, because like you got to remember, in the 50s or 60s, you look out in the universe and what's there? That's what you think. Like no one's thinking that there's this unseen component that comprises 90% of all matter in the universe. Right now we take it for granted. And like at the time, that's a huge paradigm shift. That's what she did. She provided crucial pieces of data and insight to be able to say our universe isn't what we think it is. It's actually only 10% of what's out there. So to name this telescope after her was super appropriate. Her children were very much involved in that. I think they were there at the naming ceremony. I think it's 2020 in WS Hawaii, a meeting. I remember that meeting because it's the last meeting before we all went into lockdown for the next couple of years. This was the last time many of us traveled for a few years. And I don't know if Vera's children are going to be at the unveiling of these specific images, but they've been very supportive, both of the observatory of, us trying to honor Vera with the name. And I mean, just honestly, she's deserved it for both the work in dark matter, in science, and the fact she was a first female faculty astronomer at Georgetown at her university, opened up the field to a much broader set of people. Just a phenomenal person, and like having the telescope named after her it was a no-brainer.
I'm just looking up some of the facts about the survey design: 18,000 square degrees, alternating between deep and wide. Latitude coverage is mostly southern hemisphere, but obviously, Virgo we can see in the northern hemisphere tonight. Actually, if you are willing to take out your telescope and it's not too cloudy, you see thousands of fields, thousands of times over the next decade. Where does this fit in to, say, an instrument? In the portfolio of instruments from the Keck telescopes that we have access to here, 10-meter diameter telescopes in Hawaii, how do they kind of, 5 sigma point source detection limits in the R band of 25 magnitudes or so for galaxy detection, 24 for asteroid detection? What does that mean to a layperson? Let's describe it. How faint sensitivity can Rubin achieve? And is there some way to characterize that compared to what an amateur astronomer, a brilliant amateur astronomer member of my audience might be able to appreciate?
The naked eye sees roughly down to 6 magnitudes, 6 or 7, depending on. My eyes definitely don't see 7 anymore. Every magnitude is 2.5 times fainter than the previous one. So amateur telescopes, let's say a semi-professional class, 0.5 meter, will take you to 20th 21st if you really spend a lot of time. With Sloan Digital Sky Survey, we could regularly go to about 22 and a half. That is 20 to 22 and a half. That's 5-6 times fainter, but over the entire sky. Here, we're going another roughly 3 magnitudes deeper. So from 22 to 25 in 30 seconds. These are 30-second exposures. So that's the difference. It's a single exposure that's 30 seconds. You could almost hold up your own phone camera for 30 seconds and be still enough to take an image, not hours. And then we're not just doing one 30-second exposure and then moving on, never come back, but we come back every 3 nights. And then we can add those together over 10 years. So that's roughly about 1,000 images of every pointing in the sky that you can add together. So you take those numbers. So that's going to be 1,000 images, 30 seconds each. That is 500 minutes. So that ends up being almost 10 hours. At that point, you get to 27th, 28th magnitude. So these are the kinds of things that you can look up, things like the Hubble Ultra Deep Field, like things where we're major national projects to get to just a small sliver of the sky to go that deep. By the time Rubin has finished observing, we'll have that over half the sky. And again, this is a data set that as it builds up, is available to everyone. So it's not just half the sky to that magnitude for me and you. It's for like every astronomer that has a good idea.
And here's what really blows my mind about this whole discussion. We're talking about the Virgo Cluster, 56, plus megaparsecs away, just incredible. We can start talking about redshift, a few 0.005 or something like that. We're now in the Hubble flow, getting close to it, 54 million light years distant, accidentally discovered by a comet seeker. And something that might not have occurred to many people is that this instrument, which can do cosmology, galactic science, what I was researching before the call, these mergers that you talk about, astronomers call them galactic harassment, which is just quite a silly name in my opinion. But in just that 10-hour period of looking at the sky around Virgo, Rubin found 2,000 new asteroids. 2,000, let that sink in out there. In 10 hours, that's, if you just do the raw math, at 1 every 18 seconds. And to put this in perspective for the viewers, the entire world in a given year might discover only 10 times that. Rubin, in 10% of that time, in a single night, equivalent of a single night, while it wasn't it was on the menu to detect these things, but it was doing other things. It was sort of serendipitously, while it's looking at galaxies billions of times farther away than anything in our solar system. And what's terrifying in some sense to me is that we know of the locations of only about 30,000 asteroids. Most of them are harmless, but based on what Rubin has demonstrated, there could be maybe 1 million asteroids out there that we have absolutely no idea about. Nothing about their properties, their mass, their size, their trajectories. And we're flying blind through this cosmic shooting gallery, and we didn't really know about it. So, Mario, when Rubin fully goes operational soon and starts its systematic sweep of the accessible sky, we're going to be in for a shock based on what you showed me. So can we take a look now at some of the time varying, the asteroid discovery revolution? There's no other way to really describe it, right?
It's crazy to me that we now have the technology and the computing and the software to build a telescope where the same telescope gets used by you and me. So you, in the sense, a cosmologist, somebody who cares about the universe as a whole, and me, with my current hat on, I'm super interested in the solar system. And it's exactly the same data set. So let me show you this. I zoomed back in on M49, and one of the things you see here is that these are mostly galaxies. Some of these dots are stars. There's a big galaxy. There are no asteroids here. We spent a lot of time carefully removing them from these images. So I'm going to go and show you the image with the asteroids. Look at all these little lines that you see here. There's a line here. There's a line here. There's a line here. Those are asteroids. And remember, these images are produced by taking a number of exposures, number of snapshots of the sky, and then adding them together. And we can do that because galaxies don't move, at least not fast enough. Asteroids do. So as we take these snapshots, asteroids move from point to point to point to point. And that's why instead of them all, nicely posing for us statically on a single image and combining themselves to their real color, individual color images get spread out like this. And instead of one dot, you get a nice little trail. So this here is one of many asteroids. You don't even try to remember their names anymore. Here's another one, and they're everywhere. They're like, you can't, like, this is one, this is one. There are many, many faint ones that you don't even see that don't survive this correlation process.
It's appropriate when I look at that. I think, the famous phrase, "My God, it's full of stars," and that's from Arthur C. Clarke's 2001: A Space Odyssey, which is where the pod bay doors over there comes from. But it's also where the word podcast comes from, right, Mario? Did you know that?
Oh, I didn't know that.
Vinny Sirico is an engineer at Apple who showed Steve Jobs the prototype iPod, and remember had that little circle on it, kind of like, and it looked like one of the pods in 2001: A Space Odyssey. So, my podcast, Into the Impossible, named after Arthur C. Clarke's famous phrase, "The only way to know the limits of the possible is to go beyond them, into the impossible." So it doesn't appear in the film, but it does appear in the book. My God, it's full of stars. When I see these images, and you're about to see them out there, I say, my God, it's full of asteroids. Take it away, Mario.
I was so tempted to reply, it's actually full of galaxies, but we're not allowed to say anything about what is beyond the show.
Well, now, by the time this comes out, you are.
Full of asteroids as well. So this is an asteroid crossing over a background galaxy. So here now, we're not co-adding all those images, but we've put them together in a movie, and you can see it floating by. And now you're going to ask me, like, what are all these gray things that come in on the sides and so on? Well, sometimes the camera is going to be right at the edge, or the asteroid is going to be right at the edge of the camera, and that's where a piece is missing. Sometimes we're going to get a satellite trail coming across, and that's where, you might see like a long tail missing. Like you're kind of seeing here how the sausage is made a little bit, which to me is fun, but that's like a quarter worth of a course to discuss the details. But here's our asteroid. And as you said, we found about 3,800 of them, of which 1,800 are known, and so I think 3,900, of which 1,800 are known, and about 2,100 are unknown. And so for every known asteroid, we see an unknown one. So that means if you just extrapolate, you just assume that's how things are going to be for the next year, that means we're going to take a circle around the sun with the Earth taking us around. And if for every known asteroid we find one more, we'll double the number of known asteroids in about a year. And it's actually going to be better. Because remember how I told you that these images that we took, they were all taken within 2 weeks of the first ever image taken by this telescope. This was before we tuned the telescope. The telescope is not even fully in focus yet. We can do better. So everything that I showed you is just, engineering data that we're using to actually tune everything. So like just take that and multiply it by some factor. We expect to go from 1.5 million known asteroids today to about 5 million by the time Rubin is done.
Talk about the challenges of data analysis. What are you facing here? You're a known expert in this field of huge amounts of data processing. What's going into it? Is it, a single grad student, coding in Python? Is it some, vast GPU cluster somewhere? What are the computing hardware and software requirements and just data management of this vast data set?
To give you a sense of things, Sloan Digital Sky Survey was one of the groundbreaking surveys early in the 21st century. It imaged, I think in the end, about 60% of northern sky. A lot of first results about baryon and acoustic oscillations came from, and about understanding the cosmic power spectrum came from SDSS. It's as well cited as the Hubble Space Telescope. Hugely impactful. Sloan took about 10 years to collect 20 terabytes of imaging data. Rubin does that every night. And we're going to do that for about 3,000 nights. So in terms of computing, we're going to be accumulating on order of 6 petabytes of raw data per year. When you perform the analysis, that expands by roughly between a factor of 5 and 10. And so we're going to be generating data sets that are on order of 30 petabytes or more every year. So over the full 10 years, it's 60 petabytes. The kind of computing that you need for that right now, for real-time computing, things that have to happen during the night, it's a relatively small cluster. We only need about 2,000 cores. For the large scale, like what I've shown you, to take all the images, add them together, understand the shapes of galaxies, understand where dark energy comes from, there you're coming into tens to hundreds of thousands of cores working in unison to process these data sets. So just the raw compute is significant. That compute, that those CPUs have to run something. And we spent about the last 10 years or so working on algorithms to really find all the asteroids, find the comets, find the variable stars, find the galaxies, measure shapes of galaxies, understand how they evolved through time. By this point, I think that's somewhere around 7 or 8 million lines of new code. Most of it is in Python with the key components that have to run fast in C++. The number of people who have worked on Rubin data management, the group is on order of 200 people. That includes everything from hardware to software. In software alone, I think we've got about 50 or 60 people working on it. Most of these are PhD astronomers. This is a very unique field. It requires you to understand the astronomy and to understand the software engineering to put all this together. And then this is spread out over about half a dozen institutions in the US. And the computing itself is very much an international project. And so our main computing center is at SLAC in California, with 2 computing centers in Europe, one in the UK and one in Lyon, France. Then you can imagine all the networking that it takes to move data around and so on. This is really, the project I would compare this to is maybe something like LHC, the Large Hadron Collider, and how they do their data analysis and knowledge extraction. One of the things that's different about this telescope is when you used to build telescopes in astronomy, and you know that from Simon's Observatory as well, we used to think of telescope as, give me a dish or mirror, give me a detector, and then the rest, the grad students will figure out. We don't do that anymore. We can't do that anymore. The rest, the analysis software now is as important as the mirror and the camera, or as the dish and the detector. And so about a third of all the effort on Rubin, more than a third of all the effort has gone into the software part.
Any other things you want to say about technology, your team's roles and things, or even the role of AI? I mean, are we entering a realm where this might be the last of a kind of observatory? Not just because of budget cuts and things that we'll talk about over our next beer together, but are there perhaps, does this represent a paradigm shift in how astronomers will do their craft in the 21st century?
I think we're still trying to figure out exactly how far can AI get us. And my sense is that it can get us very far. All the software for Rubin, there are parts where we're using AI, but most of the software, it comes from ab initio understanding of the processes that generate these images, rather than learning based on seeing correlations, which is what AI does. I think one of the things that's going to happen with this data set is, one, we're going to do a ton of great science, but the other, I think that it will give us the training set to do some really interesting experiments with the utilization of AI for future knowledge extraction and data analysis itself, because we're going to have 6 petabytes of data in about a year or so. And so what I think is going to happen is next 10 years in astronomy, or just in science in general, are going to be challenging given budgetary situations around the world and everything. So we want to understand how to maximize the utility of data we're collecting. And I think the first couple of years, we're going to do phenomenally well with the software we have right now. But at the same time, we'll be devising, how do we build maybe an AI-based code that goes even deeper, right? With all these numbers, and we know that historically, when SDSS started, nobody believed that you could do photometry to better than a few percent, right? Now we're looking at 1% photometry and go like, yeah, that's easy. Let's see if we can get to 0.5. Let's see if we can get to 0.1. And that, I think, is where AI is going to take us. Like all of these things that we aren't even imagining, building even deeper images, like in the solar system, discovering objects like, not like just like Planet 9, but objects could be even farther out than Planet 9. Like that might require AI to become computationally feasible.
Yeah. Can you show those Tiana, the Transnewtonian and the visualization, the segment, before we start the wrap up?
So this is an animation when we add a third dimension to all the asteroid discoveries. And so what you see, all these dots over there, each one is an individual asteroid. And now we zoom out away from the Earth. The blue line that you see here is Earth's orbit. The bright thing that's coming in at the bottom is the sun. And that gives you a sense of scale and where these asteroids are in the solar system. So most of them are here in the main asteroid belt. Those are these blue ones. And if I rewind slightly a little bit back to the front, like here are the near Earth objects. Note how closer these are to the Earth. And then these violet ones out here are the trans-Neptunian objects. They're the distant ones. And who knows, there might be a night planet somewhere out there. And if it's there, I think we have a pretty good chance to find it.
Wow. Well, speaking of asteroids, remember you can win one of your own if you go to briankeating.com/edu and you have a .edu email address, live in the US. I'll send you a fragment of one of those babies out there. Hopefully not an Earth crushing one. Although you might discover some of those, right, Mario?
Oh, yes. If there is one. So right now we know about 40% of what are called potentially hazardous asteroids. With Rubin, we hope to get that number up to about 80% or so. We hope to double the number of known potentially hazardous objects. And if you think about it in the other direction, in terms of risk, going from 60% unknown to 20% unknown is a reduction in risk of factor of 3. So that's the hope.
Okay. Are there any other things you want to share?
Let me just show this video. And this is a view of the solar system from the top and then on the side. And what you're going to see is how Rubin discovers objects in its first year of operations. So it almost functions like a radar beam that goes through the solar system, and as it observes, just uncovers everything. It sweeps everything out. So the red ones are near-Earth objects that you asked about. The yellow ones are main belt asteroids. Here are the Trojans that follow. They're in the same orbit as Jupiter, so Jupiter's hiding somewhere here. And this here is the outer solar system. And we're going to increase the number of objects known in the outer solar system by almost a factor of 10.
In just 2 years there. I mean, that's 2 years from today you're showing that.
Yeah. All of this happens in the next roughly 2 to 4 years. It's wonderful. We don't have to wait for 10 years. That's the beauty of, I think, solar system exploration with Rubin.
Are there potential military or defense applications of Rubin? If the government, decides they want to, see what Iran is up to in space or something, has that been discussed? Is that something that, you could talk about? Or?
I don't think so. Telescopes at this scale, our government already has tools to look for things in orbit.
You did mention something, the LHC, a few minutes back. And I think, what you have revealed today in the press conference was sort of like an LHC moment from, 2013 when the Higgs boson discovery was announced. And I had my kids that were, at least the ones that were alive back then, I made them watch the press conference so they could say they were there. And hopefully when the Simons Observatory gets a first light moment, they'll be doing the same thing. Let's zoom out, because I think this is as I said, a paradigm shifting moment, because Vera Rubin is not just about galaxies. It's not just about asteroids and so forth. It's not about the Lagoon Nebula only. It's about a new type of astronomy, multi-messenger astronomy. It's an observatory that, in conjunction with other collaborators, including Simons Observatory eventually, it can work with CMB data, supernova data, and very excitingly, LIGO and Virgo and the detections of, say, black holes, 500 million light years away. When that's announced by LIGO, Rubin can automatically slew there to within 30 seconds to catch the afterglow. And as a professional astronomer, I'm really fascinated by all the stuff you've talked about today, but as a curious citizen, as many of my audience members are, I'm really wondering, what does it mean when humanity can suddenly have real-time alerts about the most violent events in the universe? When you guys are characterizing and cataloging billions of objects, phenomena we've never imagined at high signal to noise, we're entering, a new era where discoveries were going to happen daily instead of once per decade. And I'm worried in some sense, if you can use that word, that humanity, like the second moon landing, wasn't really watched by, more than the square root of the first moon landing and so on. Like, will we become inured to this kind of spectacular realizations that occur, on a daily basis? What kinds of civilization-changing discoveries might be hiding in the data that we don't even know about yet, Mario? What are you most excited about, the serendipitous things?
That is the fate of man. You get used to the good stuff. With Rubin, it's going to be just like that. We are now at the precipice with Rubin, with Simons, with all these other observatories that are now, they're on their own, they're fantastic. But the other thing that I think people don't quite realize is that we now can all operate together in almost like a network. When the LIGO finds something that's interesting, we can get an alert within seconds after that happening and redirect the telescope there almost entirely automatically. We can collect a lot more data from very interesting, very unusual objects than we have before. The LIGO example is something that we're actually trying to test, I think, over the next month or so, just that entire system. Where I think this leads us is with the sheer numbers that we're going to have. We expect to observe an order of 40 billion objects, 20 billion galaxies, 20 billion stars, and then millions of asteroids. It means if you have a phenomenon in the universe that's occurring once in a million, we're going to have 40,000 of those. If you have something that happens once in a billion, right, we're going to have like a couple of dozen of those. So we're going to be able to look for incredibly rare things. And I think for the first couple of years, we're going to look for incredibly rare things that we expect, but then we're going to just be overwhelmed with things that we didn't even think about. And that's the sort of thing that's always happened. That's why these projects are interesting, right? Every time you go and explore 10 times more of the universe that you've explored before, you're going to find things that surprise you. Like, this is how we came back with dark energy. This is how we came back with dark matter. This is how exoplanets came about. Like, many of these things that we just take for granted today were not supposed to be there. It's like, who ordered this? That type of thing. That with Rubin, we're going to be in the who ordered this scenario, hopefully in the next couple of years. And so everything we talked about today, yeah, we're going to do that, but that's probably not what Rubin is going to be famous for. It'll be something that's completely unknown. So that's been the history of astronomy, and that's why we really want to push forward and deeper and deeper with these kinds of telescopes.
And what a fitting tribute to Vera Rubin, her legacy, her name, and to the curiosity that she exemplified and that you do as well. And I just think how lucky the community is to have you and your colleagues, your students, to bring this data to light and really launch us on this new epoch, this new era that I think we'll be remembering for all time. So Mario, thank you so much for everything you do. And congratulations. I'm so happy for you as a friend, proud of you. Couldn't happen to a nicer guy, get a nicer team. And this is just the beginning. And I cannot wait to see where this appetizer leads us to the main course over the next decade.
Thank you, Brian, and very much appreciate you saying that. And yeah, I want to stress that this is just the beginning. Like, everyone here who's watching this, go take a look at this data set and start thinking what you can do with it.
We'll have links below, and this is a citizen project. You paid for it out there, so take it, well, at least if you live in the US. But no, there's European partners too. Don't let Mario and folks like me have all the fun. Mario, thank you so much.
Thank you, Brian.
This has been a landmark year in astrophysics, and Rubin is only making things more exciting. Click this video to hear past spokesperson of the DESI experiment, Kyle Dawson, explain exactly what DESI found and why it's upending our understanding of dark energy. Click here and don't forget to subscribe.